And no, you gotta send it. You gotta send a follow up to like no, but that's what I like about making good. Yeah, I think very rarely make hundreds. If I make a choice, I got to check and say,
Okay, let's get started for today. No quiz today. Maybe Thursday, we'll see. Didn't have time to make one today. So. All right, so last lecture, we finished off on matrix multiplication, okay? We wrote like a very, very simple kernel. We started out, this was the CPU code, right? On like how you write matrix mul. You've probably written this in your under. Pretty straightforward triple nested loop. We took that thing and then we basically turned it into a grid. We talked about the different ways you could sort of cut up the grid. Depending on how big your matrix is, you can assign different block sizes and then have different numbers of blocks to essentially cover every cell in your product matrix. And in this simple implementation, every thread is just computing one cell in your product matrix, which is basically performing a dot product on one row and one column with two inputs. That is the math for matrix multiplication. And then we talked about different ways you can cut it up, pretty straightforward. If you had a 16 by or an 8 by 8, you can make your blocks either 4 by 4 in this trivial example, or 8 by 8, 4 by 4 or 2 by 2. And again, that is some flexibility that you have as a programmer as you sort of tile your problem. And then we talked about the code itself. Okay, I'm going through this fast because this is all just a review of what we talked about last lecture. And then this was the actual Cuda program that is the very basic translation of matrix multiplication running in Cuda. And you can code this up and you can run it and it'll work, okay? And this is a simple code because it's making an assumption that the matrices are like the same size, right? This is only going to work on square matrices. You can make this work on rectangular matrices with some if conditions to basically, bound things and allow, a different width and length based on the size of the matrices. Are there any questions on this? Okay, hopefully fairly straightforward. We pointed out some of the basic things we did to help the compiler here. What did we do to help the compiler in this code? Yeah.
We added a p value to store some in Scratchpad.
Close. Everything you said is right except for the last part of your sentence. Yeah.
For register allocation, not
in the register, not Scratchpad. So to store things in Scratchpad, we're going to see how to do that today. You need to explicitly say that with the keyword shared. When I just created this float, here we go. Where is it? So yeah, I just created this float. So he's correct in pointing out that like this was helping out the compiler. This goes in the register space. So basically your compiler is going to allocate a register for this thing. And the upside here is that this loop, again, sorry for the formatting. I always mean to fix this and always forget, but like that second statement is not actually inside the loop, right? So the loop is going through and it's aggregating the value in p value to compute your dot product. And then every time it reloads and restores to p value, that's in a register. You could have just put this, okay? You could have put this statement, which is the output matrix, the output product matrix in place of p val, but your compiler will then generate stores and loads every time you go through this loop, and it's going to just trash performance. So this isn't the absolute stupidest way to implement matrix multiply, but it's like the second most stupid way. Because at least we're not doing load, add, store every time. You sort of put that in the register by helping the compiler out. Questions on this? Yeah.
Is there a difference in having to float the initialized inside or outside of the if statement?
It doesn't matter. So the only difference would be the compiler's smart enough to probably dead code eliminate. Well, no, because it's a runtime value. So the difference would be if you don't go into the if statement, you're slightly faster if you put it inside, right? So like I don't have to initialize, the compiler won't have to initialize p-value to 0 for those threads that are actually not passing that condition. It's a trivial micro optimization that means nothing. So you can put it inside or outside and it really won't make a difference. But do you understand what I mean? Because like some threads won't go into the if. The threads that don't go in the if you put that statement outside, they have to run that float initialization, even though they don't use the value. If you put it inside, then they don't. So one less instruction in threads that do no work. Okay. Other questions? Not really super helpful, but that's what would happen. Okay, so now we started to allude to this, and we haven't actually, covered it in. These slides have some weird timing thing that I don't know how to get rid of, so they jump on me sometimes. We started this discussion on the boundedness of the program. Okay, I think we probably had this discussion. So for that very simple program, is it memory bound or compute bound? Guys remember what we said or have an intuition on whether it's memory or compute bound? Maybe we didn't talk about it, or maybe everyone forgot. Here's the kernel. Okay. In a GPU, do you think this is memory bound or compute bound? Who can define what I mean by memory bound or compute bound? Does everyone know what those terms mean? Everyone want to take your shake, you're up and down like yes, so you want to volunteer? What does it mean to be memory bound or compute bound?
Which operation is the slower one? If compute is waiting for memory, then it is memory.
Right.
Memory. If you get data faster, then you get a very big.
Right. So basically, which of these two broad resources, right? Compute is your ALUs, memory is your memory bandwidth from your HBM memory. Which of these two things is the program's execution time bounded by? Okay. And in GPUs, in CPUs, this is a little more nuanced, right? Because like there's only so many threads. So, the individual threads like latency actually plays a pretty big role. But when we talk about throughput processors, we can sort of assume that we can scale up the number of threads to be as big as we need to, okay? In these sort of thought experiments on whether you're compute or memory bound, okay? So there's no lack of work, right? The problem in CPUs is that sometimes there's not enough work in each individual thread and weird things happen. And these weird microarchitectural side effects like branch mispredictions and all this other crap happens. And GPUs it does not happen. But we can sort of make a simplifying assumption that we will always have enough work if our input size is big enough. And if you take that as a thought exercise, what do you think you want to be? What is a characteristic of a well-optimized program? Do you think a well-optimized program is compute bound or memory bound? Compute bound. Why?
Because that's like the whole point of a GPU.
That's the whole point of every computer, right? All of this stuff is just trying to get you to do more math, right? At the end of the day, your machine is bounded by how many operations you can do on each cycle. And if you have made your workload compute bound, you literally cannot push more work into your ALUs every cycle, and your program is perfectly optimized. Okay, so in an ideal world, the program is compute bound, meaning that the compute units are never waiting for anything. They're always just firing away because they've got work ready. Usually poorly optimized programs are memory bound because the programmer hasn't taken the time to keep all the ALUs busy, okay? And you'll see this when you code stuff up and when you look at sort of boundedness of programs in general. If memory is a problem, then usually they're not really optimized, okay? So for this code, what do you think? With all that context, who wants to, flip the proverbial coin and guess which one this is? Yes.
I'm gonna guess that this is compute now.
Okay, why?
Because you're doing only because you're only doing like if you look at stores versus many multiplies and accumulation.
So we did this thought exercise at the end of last lecture. What is the compute to memory ratio of this piece of code? Don't remember? How many bytes? So we would measure this in bytes per flop. Okay, what is the bytes per flop ratio of this code? So we do some counting. Okay, 4 bytes per flop. How did you get to that number?
12%, 8 bytes.
So 8 bytes to be loaded because I'm loading, like, look at the inner loop. Okay, this is where the program will spend all of its time. Like, who cares about this other crap? Like, programs are defined by their inner loops mostly, usually, right? So the inner loop here has 2 loads to global memory, the DM and DN, each of which is loading 4 bytes. So there's 8 bytes total. And then how many floating point operations are we performing? 2, right? We're multiplying and then we're adding. So there's 2 floating point operations for every 8 bytes of memory loaded. Okay. What do you think you get, like, just from a sheer, you guys kind of know how computers work standpoint, right? Like, we clock cores at gigahertz. Okay. So at a rate of 2 gigahertz, I'm going to be able to do 1 floating point operation on 1 core or on 1 lane in my GPU. Okay. The memory to go get 8 bytes from memory for every 2 operations. Okay. So every 2 operations takes 2 gigahertz, let's say, on a conservative GPU. That's half a nanosecond. So I get a nanosecond worth of execution time to do those 2 operations. Do you think I can get memory at a rate of 8 bytes per nanosecond from modern DRAM systems if I'm missing in my local cache? Not a chance. Not a chance, right? So this is going to be memory bound because the rate at which we have compute, and again, you can design weird machines where maybe this is compute bound, right? If you had like a really 1 compute unit and then a giant memory system that was low latency, it's possible. But on a GPU that is just stuffed, jam-packed with as many ALUs as we can get, yes, there's a lot of memory bandwidth, but we cannot scale memory bandwidth at the same rate that we can scale compute. So as a result, the machine leans more towards having more compute inside each kernel. There's a question.
Why are we not including the store as part of this?
So just to simplify, so there is a store there. Stores generally, since they're not on a critical path, right? You can kind of elide them mostly, and this one isn't even in the main loop, so it's just simplifying assumption. Yes, there is an extra store there, but the program doesn't have to wait for the store. Yes, it'll soak up some memory bandwidth, but it doesn't have to wait for it to complete to do anything else. So we just ignore it in this example. But good question. Other questions? So this kind of high-level analysis is very useful, in particular when you're doing GPUs or any kind of accelerator. You sort of trying to make these assumptions about like, what is my relative compute density? There's a good paper on this from UC Berkeley, a guy named David Patterson. You guys heard of this guy? Hopefully, yes. He wrote the textbook that hopefully you all looked at. It's called roofline analysis. It's not specific to GPUs or accelerators, where they basically look at, you look at the operational intensity of a workload. And then you can basically plot it on an XY axis of like, okay, this is how many memory accesses it's doing, this is how many flops it's doing. And then you can get these sort of very high level analyses of very different types of computer systems based on what their compute to memory ratio is, and then how the workloads are behaving on those platforms. Not something we're going to get into any depth in this class, but I'm going to expect you to be able to analyze CUDA code and tell me what are the memory and compute characteristics of it and how you might make this better. Okay, so this is going to be memory bound, and let's just concretely study why here. Okay, so here's our picture, right, of our system from the programmer's perspective, and just a summary of what we talked about in terms of the ratio of memory we're going to read versus compute we're going to do. So if we assume there's no caching, which is a fair assumption if you've got no locality, where you just have so many threads that your caches will crash. That means you're going to need to read 8 bytes, as we said, of memory for every two floating point operations, which means the operational intensity here is 4 bytes. So 4 bytes, 4 bytes per second worth of memory bandwidth for each sort of floating point operation that we have. So now, oh, I hate this. Why does it do this? Sorry, it'll automatically transition for the next little bit here, and I can't seem to get it to go back. All right. So then we can look at a right. So then we can sort of scale things up. And if we scale up the memory bandwidth, we scale up the memory bandwidth, at the same ratio that we scale up the compute. So if you have 650 gigabytes per second worth of memory bandwidth on your chip, right? When you buy a GPU, it says that this thing has this much memory bandwidth. Then you're going to consume bandwidth at a rate of, 4-to-1 versus your gigaflops, right? So you can think of gigabytes per second as your memory bandwidth, and then you can think of flops, floating point operations per second, as your compute bandwidth in the limit, right? A machine, you buy a machine. Let me just do this. Here, you buy a machine, right? And its sticker has on it, it's got this many gigabytes per second of bandwidth, and it's got this many flops. Like if you were floating point operations per second, that's what flop stands for. And then if you sort of assume that your program is running and you have enough work that you can consume, bandwidth and then get compute for all of that bandwidth, you can assume that they will scale up at that ratio based on what your program looks like. So at 650 gigabytes per second, I can get flops, which let's say that Volta is limited. Potential, I don't know what the exact number of, but Volta I think might have been 650. Modern ones are around a terabyte, but this exercise is still useful. So you've got 650 gigabytes per second on the chip. If I consume all of that bandwidth, then I get 1/4, okay, of the floating point operations per second, which is 162.5 gigaflops. And the machine that I bought actually is capable, if it's a Volta machine, of 13,000 gigaflops. Okay, so you ran out of the memory bandwidth on the machine before you ran out of the compute on the machine. Okay, because the ratio of compute in terms of floating point operations per second versus bandwidth in terms of gigabytes per second is highly, highly skewed towards compute. And that's just because that's physics, right? We can put more compute on there a lot easier than we can memory bandwidth. Okay. So that simple piece of code, you look at it and you're like, okay, I've got all these compute units on my GPU and it's using 162 on 13,000, or like 10% of the flops that you could get is being consumed by this very simple kernel. It's using all the memory bandwidth you have, but who cares, right? Like what you want is to keep the floating point units busy, and you're not doing a good job. Okay. Questions on this, because this type of analysis is important. And you can do this back of the envelope on pretty much any program. Make sense? So I'm taking the very micro gigabyte per operation and then scaling up to the macro of this is the whole machine. This is how much gigabytes per second of bandwidth I have, how much flops I have. What thing ends up running out first based on the ratio? Yeah.
So realistically, the only way to become compute bound is if you really only do like one memory access, like load, and then just manipulate the data but don't ever access them. It's like no realistic workload would.
Not true. Not true. So where the bandwidth is here is important. Okay. This bandwidth that I'm talking about is to what memory substrate? What is the memory bandwidth that you think of when you think of a GPU? What is the technology it's implemented in? HBM. Okay, this is the main memory, the 80 gigabytes or whatever there is on the GPU card you have. That is what memory bandwidth is when you talk about at a macro scale on the chip. I have memory elements inside the core that are much, much higher bandwidth than the main memory system. Okay, a cache, for example, in a CPU. If you spec'd out what the bandwidth of your cache is, even on your Intel core, it's insane, right? Every cycle you can get, a word back from this thing, and it's at 4 gigahertz. That's way more bandwidth than what you've got going to your main memory system. So the key will not be like, okay, I only have one thing, from memory generally. I still need to read and write from memory, but I can't read and write from this precious resource that is the global memory bandwidth. I need to put it in a memory that's closer to home. Okay, so many workloads are compute bound. You know, there's engineers in NVIDIA, Facebook tuning workloads to try to get them to be compute bound. And they do that by trying to increase the compute density by avoiding accesses to memory and putting stuff in storage spaces that have much higher bandwidth closer to the core itself. Okay, good question. Other questions? Yep.
So, like, if you to do that, you can just copy it and share your memory. Would there be like an initial, like, I guess, delay?
Yeah, it's like a pipeline, right? There's a cost to fill. And if you fill frequently, then you never get perfect, right? You can never be, well, you can, but you know, the only workload that would like always use all compute units every cycle since you power this thing on is like an ALU fed by 2 random number generators, right? Like you gotta wait somewhere for stuff to come from some large memory source. So it's never going to be perfect, but in the limit, if the most of your program is spent in this very compute heavy phase, then you amortize the cost of sort of filling these memories. Good question. Other questions? Yep.
Like when you mentioned 8 bytes, it means 1 nanosecond. Like 8 bytes should be transferred in 1 nanosecond. Right. Like, why is that a constraint? If we can do like 8 GB.
Okay. So yeah, because so this is latency versus bandwidth. So if you just got that one thread, yes, you know, you have, so I can increase my memory bandwidth by simply just adding more wires to my chip, right? And then my memory bandwidth gets bigger. So it's not as though, so again, maybe that was a poor way to put it, like the 2 nanos, like a half a nanosecond thing, because it sort of assumes that, you know, if you could just take that raw bandwidth number, but that bandwidth number doesn't really tell you the latency of going to memory. The actual latency of going to memory is more like 400 nanoseconds, right? So that is the problem with the ratio. This bandwidth can be scaled easily with space, but you can't scale it in time with memory. You can scale it in, you know, both time and memory much more easily on the computing side. Does that make sense? Yeah. So that's the real comparison. If I'm talking about quarter or half a nanosecond, is, you know, 400 nanoseconds. Those are the 2 numbers that matter on that scale. Does that make sense? Good question. There's another question here. Yeah.
How do you find ratios and
In this example, we sort of elided them. Okay. Yes, there would be integer operations. There's some pointer math in there. We're sort of making the assumption that this stuff is free, right? And that the floating point is really what's bounding your program. And generally, this will be true, right? Most of what you'll spend your time on is feeding the floating point. If you don't have enough of the sort of integer pipeline stuff to keep up with the demands of the memory pipeline, well, it's usually the memory pipeline feeding the floating point pipeline, then you have problems. But we're sort of making the assumption that that's sort of free, right? Okay. Other question? Yeah.
How many peak memory values? How easy it is to utilize all the?
Yeah, it's impossible. So again, this is a thought exercise. This is like a limit study. So you can perform this test. You can write this code. You can scale it up on any GPUs that you guys have access to, and you can measure how long it takes to perform the matrix operation, and you know how many floating point operations it's going to have just by the math of how many dot products you need to do, and you'll get something that's very close to this number. Okay, it won't be exact because you won't actually use all of the memory bandwidth, and there's some edge, like, you know, there's some warm up and all this other crap that's in the way, but we're talking about, you know, 5-10% difference. Order of magnitude wise, it'll be very close. But yeah, you're right. You're never actually going to get 650 gigabytes per second. Even benchmarks that people hand tune to try to just test how much memory bandwidth does this machine have, it'll never hit the sticker price or the sticker memory bandwidth that's on the machine, because it's just too hard to make sure that every pin that's coming out of that chip is lit up every cycle with data. Because there's all these kind of bizarre mapping things that go on behind the scenes that make that really difficult to achieve. And we'll talk about that later in class. So yes, you're right. You'll never actually get, if the sticker says 650 gigabytes, you're probably going to get like 620, 600 at best. And that's with a benchmark that you've hand tuned that is like supposed to just go to memory consistently with a nice, sequential access pattern. If you start doing weird access patterns, this just gets emancipated and it's just like control flow divergence, right? You have a big wide GPU, but if only one lane does anything at a time, you're screwed. The same is true with the memory system. If you're not grabbing big chunks of contiguous memory all the time, you're just gonna basically trying to sip a waterfall through a straw is the analogy. And we'll talk about this when we talk about the memory system, okay? Other questions? All right. Okay, so there's some exercises and quizzes on this kind of, high level analysis of a program to sort of figure out, well, is this memory bound or is this compute bound? And the bottom line for this workload, because we're going to optimize it, and part one of your assignments is going to be to try to optimize. It's actually convolution, which you can turn into a gem, is to basically make the kernel more compute bound. Okay, so if we want to get closer to, why did I say 1,000? Should be 13,000. Anyway, I don't know where these numbers are coming from. But if we want to get closer to the peak, whatever that peak is, then we need to make the workload more compute heavy versus memory heavy. Okay. And we can do that, basically exactly how we just talked about by using the scratch pad. We only have so much memory bandwidth at the main memory system, but we have a lot more bandwidth on this on-chip scratch pad, and so we want to make use of it. Okay, so in order to do that, we need some form of reuse. We need some form of locality. We need to be able to bring that data in and then reuse it a few times before we are done with it. If there's no reuse, it becomes very difficult to use any kind of scratch pad type memory. So if we look at, the basic memory access pattern of two threads here, and they're, accessing a vector, which is nominally what's going on each row and column, right, of your matrix multiplication, there's redundant accesses here, right? Like one thread is going to want to read this whole row, and then another thread is also going to want to read that whole same row. So instead of just having them both stride through it at whatever pace they would like to stride through, what we're going to do instead is load it into the on-chip scratch pad. So conceptually, there's a much smaller memory, right? When you take 565, or 437 even, there's this fundamental trade-off between the size of a memory and its speed and its bandwidth. And so our little tiny memory is this red thing, right? This is the scratch pad. And so instead of trying to stride through this huge amount of data, let's load just a part of that data in and block it. This is what's known as blocking. This is explicit. Okay, so in CPUs, you do this with cache blocking by making sure your loops don't run too far. In GPUs, it's much more explicit. Like I will literally have load statements that say, put this into the scratch pad. And then I'll have synchronization statements that allow the threads to wait for each other to load stuff in. So you'll do this in phases where you'll load first the first big chunk of memory you need into the scratch pad. The two threads will then read from that shared resource that's much higher bandwidth. And then you'll move on to the next phase. So we loaded these conceptually we loaded these 4 things in the first phase, right? And then we're loading the next 4 things in the second, and then we load the last 4 things in the third. And then you have to pace the program now to do whatever math it needed to do in these block-sized chunks, okay? Again, this is very similar conceptually to cache tiling in traditional CPU caches. Okay, so how do you do this? So can't draw and have it not do this auto thing. All right. So first you need to identify some chunk of the global memory that you can tile in the program. Then you need to, once you've identified the pieces that are common, you load that into the scratch pad. You're going to have to control the pacing of threads when we do this. So the way that the threads or the warps will fill the scratch pad is cooperatively. So there's some chunk of data that we know all of the threads in a thread block are going to reuse. Okay, we're going to do this. This is where thread blocks come in and really be important. Okay, the thread blocks are going to reuse data. They can share the data that's loaded from other threads in the same thread block. So we're going to go through this cooperative loading phase where all of the threads or warps are going to load that data into the scratch pad. And then we're going to have to do some explicit synchronization, because there's no guarantee on the relative scheduling among the warps in the same thread block. So to ensure that, if I've got let's say 8 warps, and those 8 warps are working on this one tile of data from my big matrix, each of the 8 warps is going to be responsible for loading 1/8 of that data. So you can load it in parallel as much as possible. But I can't proceed to the computation phase until I know all the other 7 warps have also loaded their data, because I'm going to read some of the data that they read in. Okay, there's going to be a sharing here. So in order to make sure that that works, right, and you don't just like finish your load and then blow on by and then start reading values in that scratch pad that are not ready yet because the other threads haven't put them in there, we need to use barriers. Okay. So there's a very fast hardware supported barrier synchronization that exists in GPUs. It's called sync threads. Okay. This is the word in CUDA for it. And this says that all warps or all threads within a particular thread block need to make it to this point before any thread can proceed past it. Same as a typical barrier in a CPU type programming language. These are fast, they're efficient, and you need to put them basically after the loading phase to make sure that you have all the data in the tile. Then you do all of your computation. Okay, so you load the thing into that chunk, into that little red memory in the previous slide. Then you churn on it, you do whatever compute you needed. So there's reuse in this phase because multiple threads are going to be reading from that chunk. And then you have to wait again. Why do I have to wait again before I move on to the next chunk?
Because some of the threads may not be done.
Some of the threads may not be done with their compute, right? Because I need to reuse this chunk of memory, right? This scratch pad is not infinite. I have a finite amount of it. So I'm going to load a block of data in. I'm going to do all the compute I need on it. And then I have to wait after I'm done with my compute for everyone else to finish with their compute because I need to go into the next phase and load the next block, right? And so there's going to be 2 points here where we have to make sure that they proceed at the same pace. And again, the reason why we do it this way is because the data loading is explicit. It's not like a CPU where if you're wrong, it's a cache miss. If you're wrong here, it's wrong data, and the algorithm, it's functionally incorrect. So you have to make sure that they pace themselves at the right cadence. Is there a question back here? No. Questions on that? I'll see what the code looks like in a second. All right. So here is the sort of big, this is the general operation again. So we basically got, rows and columns. And instead of thinking about each thread as just going through, its own, I'm not going to be able, well, let me see if this does. Instead of just like worrying about what each thread is doing, right? That's what we were doing before. Like I was only concerned with one thread did. Now I'm concerned with what one block does. So a block of threads is going to compute a block of product cells in the product matrix, which means it's going to need to move through a block of M and a block of N. Okay, so since we're synchronizing all of this business now, all of the threads in the same thread block are going to proceed through the matrix A, M, and N at the same pace, because we're going to load a chunk of M in and we're going to load a chunk of N into this scratch pad. We're going to do all the partial products we need for that chunk of the matrix, and then we're going to move on to the next chunk of the matrix to do the next partial product. Okay, and each individual thread's partial product, where do you think that's stored? Any guesses? Yeah, in the registers, right? So all the partial products for each individual thread, they're private, right? Because every thread is computing its own output element in this case. So the partial product that each thread is computing is stored in its register. And then we're loading in these sort of shared accesses to M and N into the shared memory scratch pad, okay? Questions on this? That's conceptually what's happening. So we're going to move through this block by block. So we're going to take a chunk of M and a chunk of N, do the math on it, then move to the next chunk of M and chunk of N, do the math on that. And each time you're going to move by this sort of block size elements every time you're done computing with, a block. So, the loops are going to look a lot different here. All right, loading the tile. So you could do this in multiple ways. You could have just one thread, I guess, if you wanted, go ahead and load every element in the tile, but that's inefficient. You could also have one warp load every element in the tile, but again, that's inefficient because you actually do have the whole thread block has to wait for all the data to be loaded. So let's use all the threads in the thread block to load all the data into that scratch pad. So that's what we're going to do. We're basically going to do this big cooperative load where all of the threads in the block are going to load into this scratch pad, and they're going to load one element of M and one element of N. Okay, so it works out nicely because they're each doing, one block of P, which is the product matrix. And for one block of P, you're going to need, one element of each of M and N, and that's what they're going to load into the scratch pad. So conceptually, this looks like this. So we have this is the shared memory. Shared memory is a synonym for scratch pad in NVIDIA parlance. AMD calls this local data store. Okay. Scratch pad is what it really is, a non-tagged memory space that's managed by the programmer. So in the beginning, in this simple example, we've got 4 threads. So those 4 threads are each going to load one element of M and one element of N, get a corresponding correct products. And then we're going to, you can see the reuse here, right? So if we look at, when they're actually trying to do the partial product, these are going to be read, 2 times by each of the 2 products as it sort of goes through and computes the product matrix. Okay. So does this move? Yeah. So basically it starts up here where you read one part of the shared memory, then you move down to the next parts of the shared memory, and you're getting reuse here, right? Because before we had to go to the global memory to read these things redundantly. Now we loaded them once, and in this tile, each product can read from the shared memory, which is much higher bandwidth. Okay. And then we move on to the next phase because you're not done, right? After you finish with one block, all you've got is a partial product inside your matrix. So you have to move down and over, right? That is what matrix multiplication says you need to do. You go to the next chunk column-wise in row-wise in M, and then the next chunk column-wise, well, I guess it's inverted, but you go to the right in M and you go down in N to get the next piece to compute the next part of the partial product. And then you churn on it again, okay? Like this. Synchronization does have some side effects. You are intentionally slowing the pace of the threads. So, there's kind of a trade-off here on how big you make these blocks. Okay, the bigger you make the blocks, what do you think that does for locality? Do you think that makes it better or worse? Yep, better. Makes it better, right? The more threads you have actively participating in the block, then the less individual chunks of blocks you need to load, and the more reuse you get out of each individual block. So if you counted the number of loads to global memory that you need with small blocks versus big blocks, it's much less as the block gets bigger. The trade-off is that as the block gets bigger, now there's more threads participating. When there's more threads participating, there's more opportunities for barrier synchronization to slow you down a little bit. Okay, because if your warp is if your block is super big and it's got 32 warps, for example, then the skew between when the first one hits the barrier and when the last one hits the barrier is going to be longer than the skew if you only had 4 warps, right? So you're going to lose a little bit more in synchronization. Now, this is kind of a micro optimization. It turns out for this type of workload, it's usually better to just have bigger blocks as long as the occupancy is fine. But it's also a reason why it doesn't scale perfectly as the block gets bigger, because there's these synchronization trade-offs that you have to maintain. And this is a nice visualization of things not synchronizing. Now, if this says threads, in reality, it's warps, right? It's a whole warps reach the barrier, and whole warps wait when you're doing these kind of things. Questions on this? All right. So how do I do it? How do I actually write the code? You guys are going to have to do this. Has anyone written the shared memory program yet for their assignment? Not yet. I think you have just 2. Okay, so maybe a couple of folks. So I need some way to tell the compiler that this is scratchpad. The way that this is done in Cuda is something called __shared. This will tell the compiler that a particular variable or a particular array should be allocated inside of the scratchpad. And that's basically it. We already talked about these other qualifiers. You don't have to have __ device in front of __ shared. It's implied that if it's shared, it's device, etc. And this is also a nice sort of overview of the lifetimes of each of the individual spaces that you have, okay, and the scope, right? So if you just do a local var, that's going to be thread private. It's going to essentially be a register if you don't have any qualifiers in front of it. Right, so the memory is register, the space is, the scope is thread, and the lifetime is the lifetime of the thread, okay? Which means that this variable persists as long as the thread is alive. That's what lifetime is. Shared is a little bit different, right? So its memory is shared memory, okay, it's the scratch pad. Its scope is block, meaning that it's visible to other threads in the same block. So if I load something into shared, another warp or thread can read it. That's not true of these local variables, right? Those are private. If I load something in there, another thread doesn't get to see it. They have to load it themselves. So the scope is block wide. So there's a visibility here to allow for this sort of cooperative work. And the lifetime is also a block. So if you have a block that has 32 warps in it and 31 of them finish, it'll still keep the shared memory space until that very last warp finishes, because it has to wait for all of the warps in the block to be done before it can not only release that storage. Global is obviously, this is what's in HBM. It's grid wide and it lives as long as the application does. Constant memory is the same type. It lives in this sort of special constant place. Questions on this? Okay. All right. So the actual process here is not really all that different from optimizing it in the CPU. You're using cache tiling, but on GPUs, everything is a lot more explicit. And you have to make sure you manage the synchronization, or else you have functionally wrong code. In the CPU, if you do your blocking wrong, like I said, all it is a performance bug. If you do your blocking wrong or your synchronization wrong on a GPU, it'll be a multi-threaded problem, right? It'll be right sometimes and wrong sometimes, just based on, randoms, peculiarities of the schedule. So you have to make sure that you're actually synchronizing them properly. Okay. Questions on tiling. So you guys are going to have to do this for a couple of different applications, I believe. Let's go to the next one. So we just will do. Okay, so the next is the code. Okay. So how do we write the code for this? Row column, we sort of do in a similar way for each thread, okay, because each thread is nominally still operating on one row or one element of P, which is signified by a row and a column. And, on each sort of in the loading phase, what's going to happen is every thread, is responsible for one, like every thread is one of these little orange or whatever, right? That's the thread is responsible for this product. So this thread is also going to be responsible for this part of M and this part of N. Okay, so it's going to load, corresponding to whatever its ID is, that portion of the M matrix, and then it's also going to load, that portion of the N matrix. Okay, and the way that you get at these is through thread index in threads like this. Now, you may not be able to do it like this in Cuda, because if you allocated a big linear array for your matrices, then you have to manually do the double indexing, right? So that you have to multiply the index by the width of the row and then move on. But hopefully you guys get the picture. Okay. So when you move to the next tile, what happens? Again, you're now moving on each iteration. You're not just moving one element like you used to be. You're moving one whole tile when you sort of do the next load. So the next load has to move over by one whole tile width. So, the second iteration, the second chunk of blocks that we need to load is going to come from, basically something that was a whole tile width away from the previous one. So you implement that by, moving a tile in the column direction on M, which you achieve with this, and then moving a tile in the row direction on N, which you achieve by manipulating the first part of the indexing equation. Okay. Questions on this? Makes sense? Hopefully makes sense. All right. So as I said before, when we dynamically allocate these things in memory, you don't get these sort of nice, two-dimensional arrays. You get big linear arrays that are in row major format. So to translate, access to row, this sort of doubly indexed thing, you have to multiply whatever is inside the first brackets by the width of the row. Okay. So you all know how to do this, right? You all have seen this kind of code before. You have to, because in Cuda, you can't do like a doubly, like when you do a Cuda malloc, you can't Cuda malloc like a doubly, what do you call this? Like a two-dimensional array, right? You have to malloc a big linear space. Then you have to index into that linear space using this sort of offset computation stuff. So if this is foreign to you, take a few minutes to review this after class. All right, so here's the code. It's actually not all that complicated. It's more complicated than the other one, but it's, you know, still fairly straightforward. So the first two lines are allocations for the shared memory scratch pad. Okay, the thing that is highlighted, you know, __ shared, that is telling the compiler that these arrays are going to live in shared memory. And thankfully, since they're statically defined, we can actually do the double index thing. So we can do a two-dimensional array on the shared variables that we can't do on the global variables. And so they're going to be square. Okay, so they're going to be tile width by tile width. That tile width is going to be set by the programmer, like how big do you want your tiles to be? And we need two chunks in here, one for M and one for N. And as an aside from a system perspective, which we're going to get into later in the class, and even when we talk about occupancy, what the compiler will do here is if it statically knows how much shared memory each block needs, it will embed that information in the binary. And then when it goes to schedule these things on each of the cores, it uses that information to figure out how many blocks I can put on each core. Okay. So as you scale this up, as you scale up the tile width, you're increasing the number of threads that are in each tile, which can cause synchronization problems, but you're also increasing the amount of shared memory you're taking, which could hurt your occupancy. Because you may end up in these weird situations where you get less threads on there because your tile's too big. And we'll talk about some examples of that. So the first part of this is just doing the actual allocation. Okay, it's statically allocated in this case for the shared memory. And then we compute what our block ID in the X dimension is. And these are just like shorthands, so we don't have to write it out a bazillion times. And then we compute our row column. This is the same computation that we've done in previous two-dimensional kernels. And then we're initializing our float value here. Any questions on this setup? It's fairly straightforward. On the piece of code that I'm highlighting right now. Make sense? All right. So let's go into the loop. So the first phase is a simple loop that is going to load the elements of the tile. Well, it's not even a loop, okay? So the outer loop here is the thing that's moving among the blocks. Okay, you're going to start out with, you know, the block at the far end of the M matrix and the far end of the N matrix. As I iterate on this outer loop, I'm moving a whole block in each of those directions. Okay, so the outer loop here is the block, and you can see this by, you know, the fact that it's using the tile width to figure out how many times I need to move P. So P tells us how many tiles we've moved, and there's different ways to do this indexing, but this is the way this code does it. Then it loads. Okay, so then it has these writes into these shared memory spaces. So ds_m, and the naming here is just convention. You can call them whatever you want, but it's sort of saying ds to say this is device shared memory. So I load for each of my threads. I am going to load into my specific element of M and N into this shared block. Okay, so each thread is only doing two loads. Okay, so I have a load to M and a load to N. That's what that's what these are, right? This is the load to the global memory here. And then it stores those loads to global memory into the shared memory scratch pad. And then I have to put a sync threads afterwards because I'm relying on all of the other threads to also have loaded their data before I move to the actual computation loop, which is the next loop. Okay? Questions on this? This weird indexing that we're doing on M and N, that's what I showed you on the previous slide, because these are actually linear arrays instead of like two-dimensional arrays. No questions? Yes.
Wouldn't this create a problem if the size of the matrix is not an exact multiple of the diameter?
Yep. So this is assuming that everything lines up. So real code that we run on arbitrary matrix sizes would be different. It also assumes the matrices are square. So if you want to write code that would run on arbitrary sizes with arbitrary tiles that are not whole multiples, you need conditionals in here to check. This code is aligning all that so it's simpler to understand. Okay, good question. Other questions? And the running assumption obviously is also that tile width is going to be less than width. Things should be bigger than width of the width of each individual tile. And tile width here, in this example, this is like a compile time constant. Okay, the programmer is setting this at compile time to say how big the tile is, and it's a one-to-one mapping with the thread block tile, right? So I map the tile of the memory I load directly to how many threads I have in each tile. That does not always have to be the case, but in this simple example, that's what we're doing. Good question. Other questions? Okay. All right, so they've loaded everything. After you get to this sync threads, they're done with their load. Then this is where the guts of the math happen, right? So this is the inner loop that is going to go through and it's going to compute the partial product. So again, each thread is computing its own partial product that's stored in its own respective register. But the key difference here is this, that this loop that is going tile width times is loading from the shared memory and not from the global memory. So I loaded just once in every thread from the global memory space in order to do tile width multiplication and adds in the shared memory space, which has much higher bandwidth, a bandwidth that can keep up with the core, essentially. Okay, so this is how I save memory bandwidth. I transition those loads. Okay, I basically don't do those loads to big M and big N that are in the global space. I don't do those in a loop. I do them in a loop, but the loop goes far fewer times, right? And then I do this other loop tile width times to turn on the data when it's sitting in that scratch pad. And then I have this synchronization here at the end to do precisely what I just said previously, because if some of them are allowed to finish their computation and go back into the top, they're going to start loading the next part of the tile when the other ones are potentially still doing compute. So they're going to load in erroneous values. And again, in a GPU, this will just mean that your matrix math is wrong, right? You'll print out your matrix values and it's not going to crash, but it's just going to be like garbage because you're not going to have, if you don't do this synchronization, okay? And that's it. That's really the core of how we tile this program to make it work on a GPU. Questions? Yeah.
For instances where the matrices aren't the same size, would it be faster, rather than having a whole bunch of conditionals, having different kernels and having the CPU before it executes decide which kernel to load?
You could cut down a bigger matrix operation into kernels where, you know, some of them where you try to keep the kernels the same size and then just deal with the boundaries. That's kind of what I think you're saying. Like sort of like almost like blocks, but at the kernel level. You could do that. Generally, it probably is worse than just shoving conditionals in here. The conditionals are evaluated at core speed. Yeah, there's going to be some errors in the edges, but as long as everything is big enough, none of it matters. That is the key for GPUs, right? You need enough work that most of these things in the edges don't matter. So you could do what you're suggesting, but generally it's a worse trade-off because when you do the per kernel thing, you have to go all the way back to the CPU, spawn another kernel. And you actually need to transfer data here because the partial products need to be summed at the end. So there's a communication dependency there. Other questions? No? Okay. So that's it. So this is a side-by-side comparison of what the simple thing was versus what the more optimized thing is. It's, you know, it's more work, right? You know, it's not the first thing you do when you put it on a GPU. But it's not all that complex, particularly if you make some of these simplifying assumptions. And the baseline code also would get more complex if it wanted to deal with different matrix dimensions, et cetera. But the key thing here is that, you know, I've now increased the compute density of, so that depending on how big my tile is, right, as I make my tile bigger, I'm moving more of the reuse, more of iterations in that inner loop into the accesses to shared memory as opposed to having them out in the accesses to the global memory space. Because the number of accesses I do to M and N in the global memory space is proportional to the size of my tile, right? As my tile gets smaller, I need to do more of those, whereas my tile is bigger, I need to do less in relation to that inner loop that's spinning across the shared memory. So this is tile and shared memory, and this is simple matrix multiplication. So any kernel that has reuse, this is usually the first, this is GPU programming 101. This is the first thing you try to do if you know you have reuse. You put the data in the shared memory to try to avoid these expensive global memory accesses. Okay, and your assignment makes you do this, yes? Yep.
Should all the threads be in the same block?
So no, there are different blocks, right? So you need to launch as many blocks as elements in the output product matrix.
That's the case, I think, the P value is there.
Yeah.
Outside of the block.
Yeah.
And we are moving every time.
Yep.
Then we are doing partial products.
Yep. It's maybe easier with this diagram. I don't know.
If the first time and second time is answered in two different blocks, then you will not have access to the shared memory.
So remember, the programming is product matrix centric. So the blocks that I launch are corresponding to outputs in the product matrix. Okay, so that's my thread blocks. Now, oh well, you lost the video, but actually that's the sound too. I should just plug it in. Should put in a ticket for them to fix this thing. All right. So I think what you're saying is that there's some disconnect, right? If this block is loaded from one thread block and then this block is loaded from another, bad stuff happens. That's true, but that's not what happens, right? So one thread block is going to conceptually go across each of these matrices in that outer loop in our program. Okay, so the thread block that's responsible for this chunk of P is also going to be responsible for loading these chunks of M and N.
What is making sure that this is like a from the coding point of view?
Yep.
Which variable controls?
Which variable controls this jumping of the blocks?
The same, the entire M and M within the same thread.
So that's controlled by what you're loading from M and N, right? So if we go back to the code, now that we've looked at the picture, maybe it's easier to go back here. Right, so the loads here to M and N, these are loading the, essentially this some portion of what they're trying to load is, okay, so let's go back to the product. Okay, the product matrix is, you've got a big matrix and then you're just computing one product of that big matrix. Okay, that's what the block is doing. Each individual thread in that thread block is doing one element in that small product matrix. The equation for that is this. Okay, that is my, in the big grand scheme of the product matrix, this is the cell I'm responsible for, row column. Make sense so far? So if I am responsible for row column, and the very first iteration, I'm going to be with other threads in the block that are responsible for adjacent parts of this big matrix, okay? And then when I do these loads, right? So when P is 0, essentially this gets wiped out, this gets wiped out, and I end up loading, one portion of M and one portion of N. It's a little bit screwy here because the load isn't exact, like I'm not going to load, to make the load more efficient, and we'll talk about this probably today, you're not necessarily just loading the exact same value in M and N that is your product value, if that makes sense. Like there's some you have some offset, right, in the block that is your particular product value within the group of threads that are computing all these products. In the simple case, I would just load my corresponding, X and Y. So I just use my X and Y dimension in my thread block to figure out what chunk of M and N I'm going to grab, right? That's how you do it in the simple case. This one isn't doing that because doing it that way is actually bad for memory, and we'll see that in a second. So that's why that math here is a little bit funky. We don't actually have the threads load the ones that they're responsible for only. We mix it up a little bit. But conceptually, I am going to load my one element from each of M and N. Makes sense?
Maybe I have to go to the board.
You have to just do the math on these indices to prove to yourself that this works. And like I said, there's a little bit of a twist here because you're not just doing your, they're actually loading something slightly different and something called corner turning to make the loads more efficient. And we'll talk about that in a second. Maybe it'll be a little bit more clear then. Okay, good question though. Question here.
So if all threads in the thread block are guaranteed to be on one asset,
Yes.
and if you increase the tile width to basically mean that like all the shared memory is being used by one thread block.
Yep.
Does that mean like now we can only schedule one thread block per asset?
Correct.
So is there like other than the sync threads, like synchronization performance when it decreases when you increase locality? Does that also play a big factor in it or not really?
If you don't have enough threads,
If you use up all the shared memory with one thread block, so you
Yep.
can't schedule multiple.
absolutely. So yes, it does. So we'll see examples of, ways you can hang yourself, right? Like if I have a 1024 wide thread block and that consumes even 50% plus one of my shared memory, I'm screwed, right? Because now I can't fit another whole one on there. Half of the shared memory is wasted, half of the threads are wasted, and your machine sits mostly idle. But if you cut it down a little bit, then you could have fit two on there and then it would have worked, right? So this perverse trade-off of like trying to right size the blocks is something that you have to play with to try to get it to work well. So that's good intuition. Makes sense? Question, yeah.
So is this, do we assume that the loads on the shared memory is free?
Do we assume that the loads in the shared memory are what?
Free.
Are free? In this example, yes.
Okay, so is this still memory block? Your load
That's a good question. So it depends on how big the tile is. Okay, and what kind of GPU you're running on. So it could be, if your tile is too small, it's definitely still memory bound. As your tile gets bigger, it depends on the ratio of the machine you're running on. And you can only make the tile so big in practice. So in practice, even this will end up being memory bound on a like high-end GPU, but it's much better. We'll go through the math on that in a minute here. Does that make sense? Yeah.
So do you have to consider how large this classified is when running the software?
Yep.
So that,
Yep.
yeah. So what happens? Yeah. So what happens if you make it too large? Then does just overwrite stuff?
If you make it too large, you will get a runtime error. Like if I try to allocate a gigabyte of shared memory, it's like, oh, this is good. I'm just going to use all of it. It'll just be like, okay, you don't have it. And it'll kick, your kernel won't spawn. The driver will pick it up and be like, get out of here. Yeah. Yep.
Could you give an example of difficult sizes or like a matrix size, block dimension?
So matrix sizes are huge, like millions upon millions of elements. Okay, spread over multiple GPUs even sometimes. Yeah, if you think about machine learning training, like they're massive, massive matrices. Block size usually ends up landing somewhere between 256 and 512. It's usually one of those 2 power 2 numbers that works out well. Sometimes 1024 makes sense, but again, it all depends on the architecture and the kernels that are running and how resource intensive the individual code is. And this becomes like an optimization problem for the system. But those are typical, like giant matrices as big as they come, as big as can fit. Even as big as can fit in GPU memory is too small, right? That's why you have to spread them across a whole bunch of GPUs to train them. But think of matrices that are, a third of the size of your GPU memory space. You put all 3 of them in there, so as big as it can go, and then thread blocks are, 256 by 12, depending on.
And for the tiling.
And for the tiling is tied to the thread block size. Optimized kernels will also do more than one product per thread. We'll talk about that a little bit. Like I said, increasing the register usage as opposed to increasing the shared memory usage. Like basically system programmers will pull out all of the tricks that they can to try to make use of all of the on-chip SRAM that they can to try to avoid going to memory to keep the units busy. That is the game. And that trade-off changes between generations, between matrix sizes, etc. Okay, good question. Other questions? All right. Okay, so now we have a bunch of math on sizing, exactly to your previous point, okay? So each thread block should have many threads. Obviously, we don't want one. We want it to be at least the width of a warp. If we're going to do this tile, we're going to have these squares of the matrix that we're pulling out. So if your tile width is 16, that means that each thread block is going to have 256 threads, 16 cross 16. Okay. If your tile width is 32, then there's a square factor here because there's an X and a Y dimension. Then you're going to have 1024 threads in each thread block. And so this sort of perverse, make it bigger to make it go faster thing versus like, oh, screwing up how many threads I have is evident from this sort of thought experiment. So if I do 16 wide tiles, so I can compute, what the compute density of that is. So each block is going to do 2 times 256, so 512 floating point loads, or so loads, right? Because each of them is going to load 2 floats, right? One from M and one from M, just like in our simple version, okay? And then I'm going to churn in that inner loop for some number of flops, right? After I've done those loads, okay? So I do 512 float loads from the main memory, and then I have 256 threads, each of which is doing an add and a multiply. That's the 2. Okay, let me highlight this. Some of you are squinting as you're following along with my the math here. Okay, so we're going to compute intensity, all right, just like we did for the simple program. Is everyone with me so far that each block is going to load on one iteration of that loop, of the outer loop, it's going to load 512 floats, okay? Because remember, they each load one part of M and one part of N. Then there's 256 threads, okay? So just times 2, simple. Then I need to figure out how many operations I'm going to do. So 2 is the number of operations in that inner loop, 1 multiply, 1 add. And then the loop bounds is how wide? How many times does that loop go? The tile width. And in this case, the tile width is 16. Okay, so 2 times 16, that's how many times I'm going to do those 2 operations. And then I've got 256 threads doing those operations because that's how big my tile is. So that means I end up with 8K multiply and add operations if I do the math. So then I can do that same division, right, that I did before on my compute intensity versus memory load intensity. And it ends up being 16 floating point operations for each memory load. So, and every load is 4 bytes, okay? If I make my tile bigger, as your intuition suggested, you should get better compute density, and you do, right? So if I change this to be now super big tiles, so 32 wide, I do all of that same math, and because I'm, scaling, if you look at the factors, right, this ends up scaling by a square of whatever the tile width is, and that's multiplied by 2. And this one only scales, it also scales by a square, but it's also multiplied by this extra factor, basically. One scales by a cube and one scales by a square. So the cube ends up getting bigger, right, faster. So you end up with, so the thing that scales by a cube is the compute operations, and the thing that scales by a square is the memory operations as you make the tile bigger. And the reason for that is that inner loop, right? Because that goes and adds that extra cube factor to it. So you end up with 6 floating point multiply adds per operation. Okay, so 6,000 multiply add operations, which basically doubles your. So if you double the tile size, you double your compute intensity. That's what the math basically says. Okay, so that seems good, right? Like we want the compute intensity to be greater. We know we have much more compute power than we do memory bandwidth. So this should result in a better thing. Okay. So not always true because you can run out of resources. So here's a concrete example. If you have an SM that has a finite amount of the shared memory, let's say 16 kilobytes, and this shared memory size is implementation dependent. Generally, it gets bigger. Moore's law sort of chugs along, right? We still have more transistors for SRAM, so 16K is a super small shared memory now. Now they're over 100K in sort of modern NVIDIA parts, but the same principles still hold. So the tile width is 16, so I can figure out how much each tile wants of that shared memory. I have 2 floating point values that I needed for each thread in the 16 by 16 tile. Okay, so 4 bytes. And then I need, 1 part of M and 1 part of N, and there's 256 threads if I went with 16. So that means I'd use 4K worth of the shared, 2K worth of the shared memory space. And if I have 16K total shared memory on the core, that means I can pack 8 blocks into the shared memory. With me so far, because each one is going to use 2K. Now, so then I can figure out the operational intensity of actually having 8 of these things on here. Right, no, sorry, this, it's sort of like, so you can saturate this modes, right, to figure out how much pending memory you can have based on how many threads you can get on the core. So you can soak up this much of your memory bandwidth because you've got this many threads running at the same time. If I change this to then be my bigger tile, which I know has better compute density, and I compute how much shared memory it needs, well, if I doubled each of the dimensions, it grows by the square, right? Because it's, you basically have tile width in each dimension. So now I need 8K bytes worth of shared memory for every block. I only have 16K shared memory on each core. So that means I only get 2 blocks on each core. So I now end up with less work, okay? Because I can only put 2 thread blocks at the same time on the same core. And so basically, right. And then furthermore, okay, in this example, then, if you could only have like less than 2,000 threads on the core, then you really only get 1 block regardless of how much shared memory you're using. Okay, so there's different ways that it can sort of cut you down. So these 2 slides are just to say, generally, compute density wise, in the absence of all resource usage, bigger tiles are better because you're aggregating more. You're growing at a cube in this case versus a square in terms of compute per memory access. But realistically, when we try to look at the resource consumption with realistic constraints, it's not always bigger to grow your block size. Okay. And there's this weird trade-off. Okay. There's this, basically, how many threads can you put on each core? It's dependent on all of these 3 factors, including your shared memory usage. And, you can go and try to figure out, like, based on how I size my thread blocks, what my occupancy is going to be, et cetera. And so there's this kind of nice website that some guy wrote a Python script. When I started programming GPUs, this was like an Excel sheet that NVIDIA gave you to try to like get you to figure out like how to size your thread blocks based on what generation you're doing. Now there's this website that does this, where you can sort of tell it like, okay, my kernel has, this is the type of GPU I've got. This is, my CUDA version. My thread blocks are going to be this size. I know there's this many registers per thread. There's this many, there's this much shared memory used in each block, which you can all get from the compiler for your program. And then you can take a look at like, okay, well, what, like up generally is good. It tells you, look, you can fit this many warps on each core. And then as you scale each of your resources, it shows you the bizarre things that happen as you use more registers or as you use more shared memory and how you get more or less warps on each core as a result. And you can use this to kind of right size your block size and shared memory usage based on whatever architecture you're on. Okay. And so you have to sort of play these games if you're at this level of CUDA programming to figure out how to size your blocks. And usually where they end up is where I said, right? Usually ends up being 256, 512. Those are the most common block sizes that end up being the best. Yeah. The CUDA version doesn't matter. I don't know why there's a drop down for it. The SM version matters. Okay, so in this thing, unless they change something in different versions of CUDA, but typically they don't, right? This number, okay, this compute capability version, this is the core architecture. Think of like Intel Skylake versus, Crater Lake or whatever. In NVIDIA, it's Hopper versus Volta, et cetera. So 8.6 is Hop. Well, 8.6 is old, right? So 7 was Volta, 8 was, sorry? Now, there's names for everything. Tesla means they're compute class servers that don't have GPU, that don't have video output. Okay, so there's been Teslas all the way back to Fermi, which was like 2010. So anyway, the architecture of the machine that defines the shared memory usage is this number. And each of these numbers is tied to a particular architecture in their product line. Volta, Pascal, Hopper, Turing, they each have numbers, and you can look up the mapping to those numbers. And you can run some program on like NVIDIA SMI, I think will tell you, or there's some CUDA device query thing that will tell you what SM version thing you're running on right now is. Yeah.
Like, video has insight.
So this was made, so maybe it's not updated because this was made long before Insight Compute included these kind of features.
Yeah.
I mean, yeah, the debugging tools, the profiling tools from NVIDIA now are all pretty good, and they'll probably just do this for you. So maybe I should just update it to link to that instead of this website. But like I said, this was cool when I made these slides because it used to be a spreadsheet. Then somebody made a Python script, and now NVIDIA just builds it into the profiler. Yeah. I'm over time. We're done. We'll come back and talk more on Thursday. Thank you.
I don't think. And like, I'm not even